So let's get to problem 7 now on the 10A and the first of your rapid fire for 6 through 10 on the 12A for this year's 2024 test. The product of three integers is 60. This is a really interesting question, and for those of you new to the competition series, you might notice a few things in here that happen as you're going through the problem. Even it caught me for a second, and I'll get to what I'm talking about in just a moment. So the product of three integers is 60. What is the least positive sum of the three integers? So product of three, it makes you think you probably got a prime factor. For those of you who are experienced, this should be done at a glance. 4 times 3 times 5. So that's going to be equal to 60. So now if I'm picking three integers, the product of three integers is 60. And we say, okay, I want the least positive sum of the three integers. And by the way, what I'm doing is exactly what I did. That I did not perceive things right away. It took me a second to realize once I kind of just took some path and then realized what I could do differently to make it better. Let's see what I'm talking about. Maybe I do 4, 3, and 5 as my integers. And I got, okay, well that's a sum of 12, but that's not on here. And furthermore, everything's a lot less than that. Why? So then it was like 2 times 3. Okay, well I guess I could do 2, 6, and 5. And again, I'm getting 13, which is larger than 12. It's not getting any better. It's also not one of these answers. And why are these still? How could I ever get a sum of 6 or 5? 5 alone is 5 already. And you've got the other. Oh, wait a minute. Did they say positive? The product of three integers. Crafty. They did not say positive. The test makers know what a lot of students reading will infer. And luckily for us, right, or you, if you do the same thing, they didn't put anything like 12 or 13 on. Not that I would have accepted it right away. I would have still thought about it and challenged my thinking because I want to second guess myself. And so, but they didn't put that. So none of you could have gotten trapped with it nice enough. So if you're going to get these, obviously we might be able to use a couple of negatives. Now, if I have two negatives, I'm going to need the positive number to be larger than the sum of the other two. So for example, this is the positive number here, that the larger one has to be the positive. All of this reasoning you kind of have to generate on the test. What is the mechanism by which you're going to answer this? I need this largest one to be bigger than the other two negatives. That just makes sense, right? If I had this one negative and that one negative, the sum would not be positive. And this is also what they do. The least positive sum makes you think, oh, they're all positive integers. They didn't say that. It's the least positive sum, okay? So they do that a lot. Let that be your lesson if you're new to the contest about them doing those kinds of things. So we have to have this. Let's try this 6. It's really close, except that if 2 and negative 5 were both negative, I get negative 1 as a sum, and that's not a positive sum. So at this point, we're going to need to try again. Obviously, 6 cannot be the largest number. I need to create something larger. And if I did 2 times 3 to get that 6, what's the next smallest thing I can create up here? It's probably 2 times 5, which would equal 10. So if I did combine one of my 2's with the 5, that would leave 6 and 10. How am I going to get? Oh yeah, 1. 1 works just fine as one of our integers, making this one negative and that one negative. And the least positive sum, negative 7 plus 10, is 3. Now, you might be curious, would there be some way to get a 2? I would need, how would you get that? You could check around for it again, but just trying to make the largest number as small as possible, yet still larger than the sum of the other two, you're not going to find anything that gives you a 2. And again, we get 5 here is just 5 by itself. 6 is the next smallest thing above that. Could I create a 7? No. Could I create an 8? No. Could I create a 9? No. There's not 2 3's. 10 is definitely the next smallest number that we could make larger than the other two. You can be pretty highly confident in your answer at that point. But don't be worried that you took an extra 30 seconds to check. That's what the test is all about. You definitely don't want to lose 6 points because you didn't check. Let's get to the next one. All right, and this was the question that I felt was where the AMC 12 really started to take a turn for the more difficult. Never had seen a vector sum problem that I can recall in any of the last years, so this was your new concept, a new concept for sure. I am sure that many of you might have even skipped it because you weren't used to doing vector sums, at least in competition math. So let's get to it. In triangle ABC, angle ABC is 90. So we start drawing that. Angle ABC is 90. And BA equals BC equals 2. So we put B here, A here, C here, root 2 rather. So root 2 and root 2. Points P1 all the way to P 2024, there's 2024 points, lie on the hypotenuse AC. So that A to P1 is the same as P1 to P2 and all of the lengths all the way down to P 2024 to C. In other words, you're taking the hypotenuse and breaking it into 2025 different lengths. I'm not different, but they're all like, each segment, but they're the same length. They're all equal in size. Okay? So first off, let's just pause there for a moment. You multiply by root 2, 45, 45, 90, you know that AC is equal to 2. So if I'm breaking AC into 2025 points, or segments rather, all of those segments have to be the same size. They must be all that length. So let's actually just not put that there. Let's say that AP1 is equal to 2 over 2025. That is the length. That is the length of that value. Okay, so now what? Or each of the values rather. What is the length of the vector sum? I'm going to go from B over to this point, over to that point, and go all the way to the end over here and all the way up to here and so on. So I've got all those points. I'm not going to draw them all in. They'll get crazy looking in there. How are you going to get that? Well, first, let's do component form of a vector. If you had 1, 2, and you were to add it to 3, -1, for instance, okay? Not that that's what we're doing, but you would add 1 and 3, and you would get 4, and 2 and -1, and you would get 1. That's how vector sums work. You just add the components of each part, and this would go from some point 4 to the right and up 1. And that would be the summation of these two vectors. That's a simple way of doing that concept. So for us, we've got to figure out how we're going to do that. We got to add 2024 vectors, and they're weird, right? Like, where is this point? How are we going to get it? Well, you never know unless you try. So if you take this point right here, that's P 2024, and you drop it straight down, doesn't that give you a 45, 45, 90? Because C is 45 degrees, so when you drop it straight down perpendicular, you're going to get 90. And since we know what the length of it is, right, it's 2 over the square root, 2 over 2025, because you broke it into 2025 equal parts. So then if you have a right triangle, that's 45, 45, 90. Remember, it's x, x, and x root 2. So I need to divide that by root 2. So if I look at that one that we're doing right there, with this being 2 over 2025, and you divide it by root 2, it's the same as multiplying the denominator by root 2. Now, granted, I could put the root 2 into the numerator. You would get root 2 over 2025. But for now, what's the point, right? Let's just leave that alone. But maybe it's not a bad plan. I don't know. I can't decide right now. It's late. It's like 4 a.m. here. A little past that, actually. Okay, so then what do we do? Well, that vector then going from B to that point, what would be the distance you traveled horizontally? That distance, if I'm doing B to P 2024, that's going to equal in component form the x distance would be rad 2 minus 2 over 2025 rad 2. Looks really fun, right? I mean, super enjoyable. I don't know who wouldn't like that expression. Let's keep going though, but how far up do you go? You go up the same distance that you just lost, because it's a 45. You're going, this and this are the same. This is your y travel distance. That's going to be 2 over 2025 rad 2. Okay? So now what? That's pretty nasty. Are we sure we want to do this? Maybe you skip at this point and come back later. Maybe you never come back. You're like, I think I've had about enough of that. But little do you know, the rest of the test has lots of fun things waiting for you as well. So then what? You're going to go, let's go from B, because it's going to go, all the B connects to all of these, right? So now if you went up to here for the second one, B to P 2023, what would that look like? Okay, now your length on the hypotenuse is going to be twice this one. So it's 4 over 2025. And so you're going to have divided by root 2 is 4 over 2025 root 2. So you're going to have root 2 minus 4 over 2025 root 2, but then you'll immediately go up that amount. It's right about now that you should be saying, this is so terrible and so ugly and so horrible. They must give us some relief somewhere. This is only question 7. They've got to be something where all this nasty stuff cancels out. There has to be. Otherwise, it's going to be terrible and no one's going to, it's just, we have to have faith. They're not that mean, right? They couldn't be, could they? So now let's go, if that's what's happening over here, let's go back over here to B to P1. Keep in mind that up at that point where A is, right, looking at just where P1 is here, A is up here, it's also a 45, 45, 90. And so its length again is 2 over 2025. Divided by root 2 is 2 over 2025 root 2. And same thing here, which would mean my x coordinate of that, or the first part of the component for BP1, actually, I don't know, I'll just put it here, I guess, is going to be 2 over 2025 rad 2, right? This is going all the way down to here, right? And way down here somewhere is B, and you're going to that point, which means your distance on the x direction is that distance there, same, right? Because you're going to then go up. How far up will you go? It will be this entire side, root 2, minus the top part right here. This looks kind of familiar. So you're going to go up root 2 minus 2 over 2025 root 2. Right about now, you should see the gig is up. Because when you add this x component to that x component, just as we suspected, the nasty part cancels out. And of course, we're just doing a large vector sum, so all the x components will add up. And so the next one, of course, would cancel out this one. If we take the y coordinate over here, this y coordinate of BP1, and we add it to that one cancels that one, and you still have this root 2 in front. So it looks like when we added these two kind of, if you will, symmetric terms, they're on the outer parts of our vector sums, that all that we're left with is a root 2 and a root 2. And if we again took this one along with BP2, they would do the same thing and again leave behind root 2 and root 2. So the question is, how many of these root 2's would there be after I paired all of them up? Well, consider that you are connecting B to 2024 different points. It doesn't matter that there's 2025 equal segments, it matters the number of vectors, of which there's 2024. Would there be one dead center in the middle at 45, 45, 90 right there? No, there would not. Because your 20, 25 lengths, equal lengths, this would be half of that distance. So it would be located at, if I took those 20, 25 lengths and I divided that by 2, it wouldn't be an integer. So you wouldn't hit it right on one of the vectors. No vector is going to hit the midpoint of AC. So because of that, you're just pairing them all up, and there's 2024 to pair up into 1012 pairs of 2. And so each of those 1012 pairs is going to give you 1012 root 2. It's like root 2 plus root 2 plus root 2, 1012 times. Your y-coordinate, of course, does the same thing. So then, what is the length of the vector sum? Which means you're looking for the hypotenuse of that vector sum, which is itself a 45, 45, 90. Multiplying by root 2, you're going to get 2024. And this problem, even if it took you about 5 minutes even, it's not terrible for a 5-minute expenditure, but it's definitely a little bit off-putting and doesn't feel very comfortable in the beginning. It's very challenging, number 7, and I think you're going to see a lot more challenging problems as we go on. All right, and now the next problem, which was also quite challenging after that 7, in my opinion. If you did something good in the beginning, you got a nice off-ramp of the difficulty that lay ahead. How many angles theta with theta between 0 and 2 pi satisfy log of the sine of 3 theta? Already we're getting weird. We got sine of 3 theta rarely makes an appearance with like the summation formulas. Like you have to do sine of 2 theta plus theta, which is like sine of a plus b, and then you got a double angle within it. You do stuff like that in like trig identities and pre-calculus, but kind of weird to see it here. There's a lot of work that has to go into it. Are we sure we're going to want to split that into sine of 2 theta plus theta? I don't know. Let's keep reading. Log of sine of 3 theta plus the log of cosine of 2 theta equals 0. Now, you should just think first off, I've got log rules. Log rules say when I'm adding two logs with the same base, they can be combined into one. So immediately you get log base 10 of the product of sine of 3 theta times the cosine of 2 theta, like so. And now that needs to equal 0. Oh, and now we have log manipulation. A base of 10 over to 0 is 1. 1 has to equal this product of the sine of 3 theta times the cosine of 2 theta. Now I went ahead and decided, oh, let's go ahead and try this algebraically. Maybe you did too. It gets pretty nasty. Even if you let like x equal sine of theta at some point, so you can do some substitutions and create yourself a polynomial in x and then move the 1 over, and then you look for roots, right? And you actually will find, if you did that method, I'm not going to carry it all the way out. We can cover those identities though. Sine of a plus b is SCCS. So sine a cosine b plus cosine a sine b. So if you did 2 theta and theta, you would have sine of 2 theta cos of theta plus cosine of 2 theta sine of theta. And you should know cos of 2 theta is cosine squared minus sine squared. But because I have sines out here, maybe I should convert everything to sines, which would be 1 minus 2 sine squared. So you can replace this with 1 minus 2 sine squared theta times the sine of theta. And it's getting pretty terrible, right? And so you have over here sine of 2 theta, which is 2 sine of theta cos of theta. And that's going to give you 2 sine theta cosine squared theta, again allowing the substitution of 2 sine theta 1 minus, 1 minus sine squared theta. 2 sine squared theta. Oops, almost forgot. Okay, and then it's plus that. And then all of that is still being multiplied by the cosine of 2 theta, which is again 1 minus 2 sine squared theta. So at this point, I went ahead and factored out a 1 minus, there's a plus sign here, you just can't see it. Factored out 1 minus 2 sine squared theta. So now I have 1 minus 2 sine squared theta squared, because this copy, that copy factors out to that. And inside you had 2 sine of theta plus sine of theta, which was 3 sine of theta. So 2 sine of theta here, plus sine, and then that sine of theta over there. So 3 sine of theta. And yeah, I think that was it. Maybe I made a mistake here somewhere. But at this point I said, well, maybe we can just call this, like, call sine of theta x. So I was like 1 minus 2x squared. And then you're going to be squaring that. So it's that times 1 minus 2x squared and then times 3x. And you do all this and I think you can plug in 1 and get 0, right? 1 minus 2 is negative 1. I don't know. Maybe you can't. But yeah, I might have made a mistake. This isn't really how we want to go about it anyway. The whole point of doing this is so that you can see it's terrible. In fact, I see what we did wrong, I think, too. We had sine of 2 theta plus theta. Yeah, we did do that. Okay, so we had 2 sine of theta here plus theta. Oh, we also have the 1 over there. It's not equal to 0. Yeah, so it would have probably been okay, I think. You would distribute this all out and then you move the 1 over. Anyhow, you can tell, like, it's going to get pretty terrible. And when you start to see things get pretty terrible like this, that's like a sign. It's like, hey, this path isn't for you. Maybe find a different one. They're kind of trying to help you see that's not what they had in mind. But stubborn people will keep going like this, and I'm fairly stubborn myself. So I did go down it a little bit longer, and you do find a solution. For example, you find 90 degrees works. For example, if I do sine of 270, it's negative 1, and cos of 180 is also negative 1. The product gives 1, right? So if I used pi over 2, right, which is 90, same thing, that's going to give you a solution. And so you might have thought, hey, maybe it's 1 when you got there. I did synthetic and found 1 to be a root and got another 1, and it was just no good. So eventually you say, let's stop the suffering and ask a better question. What is this? I've seen so many problems on AMC 12 trig that came down to just graphing the trig stuff. Maybe we should do that. So let's get a look at what sine of 3 theta and cos of 2 theta would look like. You should know your trig graphs. These aren't even that elaborate if we're honest. Your b value, basically I think of trig graphs as a trig b x minus c plus d. B is what's going to determine your period of the graph. And it's going to be 2 pi over b. So this graph will have a period of 2 pi over 3. So that means the entire thing will cycle by 2 pi over 3. So if I was to graph sine of 3 theta, 2 pi over 3 divided by 4 would give you your increments of the 4 equally spaced marks. So 1, 2, 3, 4. So 2 pi over 3 would be this part, but I divide that by 4 to get 2 pi over 12, which is pi over 6. So pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, 4 pi over 6, which is 2 pi over 3. Now, that means the entire sine of 3 theta cycle has to happen by that point. So if you were to go up to the sine's max value, the max value doesn't change, your amplitude doesn't change with the b value or anything like that. You're still going to max out at 1, then you'll go to equilibrium, then you'll go down to negative 1, then you'll go back to equilibrium. But all of that happens by the time you get to here. And then the cosine graph separately, it's going to complete its entire cycle by pi. So 1, 2, 3, 4, that would be pi, 2 pi over 2. And this would be pi over 2 and pi over 4 and 3 pi over 4. And what? You're going to go up to 1 and down to -1, but you start at 1. And you dip to equilibrium and then to low and then to equilibrium and then back to the high point like this. Okay, that's great. Now, how could I multiply this value, which is clearly less than 1, with that value? I'm starting off at something less than 1. As I'm going towards my peak value, the cosine value is dropping. Could I multiply those two things to get 1? We're basically saying they're reciprocals, right? No, there's no way. You start at 1 here and sine's down here. And if sine's not at least 1 and then that one's dropping, it's never going to happen that you multiply two fractions less than 1 and get 1. So then what? What about the negatives? Let's go back to the beginning. Let's go back up to here because there's a problem, right? Log, the argument, why was it in a log? Should be asking this. This cannot be negative, which means this value here is gone. That value is gone. And when you get to over here, it's between 0 and 2 pi, you'll have to go on and inspect more, I guess. So you can't have this value over here where it's negative either. 2 pi over 3, it was 4 pi over 6, 5 pi over 6, 6 pi over 6. So at 5 pi over 6, you'll be back up here. 6 pi over 6, you're back at equilibrium again. We have to find a place where they would both have to be 1 at the same time, since your amplitude is not getting above it. And that's not going to happen. 2 theta, it would have to be at 0 degrees, or 360, which is 2 pi. In order to do that, theta here could be 0, or pi, because 2 times pi would be 2 pi, 360, same thing. And then 2 pi could also get you back to 0. Are any of these values, this is a place where cosine is 1, are any of those values a place where 3 theta is 1? No. I'd have to be at a multiple of pi over 2, and you're never going to get there by multiplying by those. So there's no way that these two could ever be reciprocals. And furthermore, the value that we found of pi over 2 that worked, the problem is when you put sine of 3 pi over 2, you get -1, which means you're doing log of -1, which is not in the domain of log, meaning that the argument of logarithm must be positive. So for that reason, there's no solutions. And that's why when you start to get all the suffering of all of this, and yeah, it's cool, we're doing a bunch of crazy algebra, it gets really crazy and it's not that much fun. You're like, how do I factor all that? And it's not fun. They're telling you go do something different. Start thinking outside the box. Do we normally look at graphs to multiply two expressions and think about it? No. Do you have to do this? You could reason without it. You could tell yourself you needed the product, but the only way it could happen is if these are both 1, since there's no amplitude value. The graph is just a visual aid to help you think about that. We don't even really need to continue, the whole graph thing. So that's it. Let's get to question 9. All right, and now the last problem in the rapid fire set for 11 to 15 from our 10A, it was also 12A problem 9. Let M, I'm going to do this in 2 different ways, using 2 different methods that are not that much alike. Let M be the greatest integer. This will be important probably once maximize. There's a lot of min-maxing in this test, like where you're trying to maximize or minimize something. Integers such that both M plus 1213 and M plus 3773 are perfect squares. I mean, if they call them perfect squares, maybe we should label them as that. We'll call that one x squared and that one y squared. What is the units digit or ones place of M? Okay, so how are we going to get the greatest integers such that this is true? So the first method that you could do is the one that I started going down right away when I was solving the test. I don't do it for merit, I'm not in school, but I solve it to get a feel for what you guys are experiencing. And so you got two squares, and there's an m here and an m there. Maybe I should subtract because that would make the m go away. And it also creates a common concept in competition math. That is, the difference of squares is created. So why don't we do that? X squared minus y squared is, the 3's cancel, 7 minus 1 will give us a 6. So you're going to have 0 and 6. This 7 in the hundreds place minus that 2 is a 5, and the 3 in the thousands place minus the 1 is a 2. So you get 2560. So at this point, you did this for a reason. You did it so you could factor. Very common plan here is that you have to have this has to be an integer because you're summing two integers, which naturally is an integer. Of course, the set of integers is closed under addition. The set of integers is also closed under subtraction. We know x is bigger than y because I made it that way. This is the bigger number, clearly. And so x minus y is positive, and it will be a positive integer. So then I have the product of these things has to equal 2560. Now, at that point, I thought, my first guess just randomly was, what if x plus y was 256 and x minus y was 10? It's just like a natural product of two things, because since these are both integers, they must both be factors of 2560 that multiply to make 2560. The other thing that you know from experience when doing this is that you want the sum right here to be even. The reason is when you add the left, you have to have an even integer. The y's have canceled out, and so you get here and you get x is 133. Okay, we found something that works. The question is, though, it wants m to be the greatest integer. So now is when you develop this and you have to ask, is this going to produce the greatest value of m? And you're not quite sure, and so you just say, well, how would I know? What would be my actual objective to achieve the greatest integer? And that would be that your x squared is as large as possible. Because if your x squared and your y squared are both as large as possible, then x squared in particular, you're going to make m, if x squared by itself is as large as possible, it will make m be as large as possible. And of course, x squared is maximized when x is maximized. So you can keep going on this path and we will continue, but what I actually did on my test is I didn't perceive what I just told you when I was doing my run through under timed conditions. I went a different route and found the answer in a different way. Okay, and I will go and show you that way in a second, but what I should have done is just said what I just told you, which is that by maximizing x squared, you maximize m, and to maximize this, you just maximize x. Logical, right? So then you say, okay, well, why don't I make this 2,560 and that 1? And again, that's what we just said. That will not give an even sum, and it has to be even, because the left side will always be 2x. Well, if I can't do 1 and 2560, then the next best thing would be 2, right? So if you do 2 and you cut 2560 in half, this could be your x plus y and this your x minus y. And then when you added, you would instead get 1282, which cuts in half to make x is 641. So that's it. That's what x is actually going to be in order to maximize the value of m. And since m plus 3773, if I could write that correctly, m plus 3773 will equal 641 squared. All I have to do is subtract 3773 to get m. Do I actually want m though? No, I want the units digit or ones place. Before you go calculate nasty looking things, to do so, you might think about what it is you're looking for once more before you do those terrible calculations. So if you square a number that ends in 1, what does it end in? It ends in 1, some number that ends in 1. Great. And we're going to subtract 3773, but in reality we only care about that 3. If you have a number that ends in 1 and you subtract a number that ends in 3, you will get, as long as this is a larger number, you will get a number that ends in 8. Okay, not negative might affect that or something, but since this number is clearly bigger than that, then you're going to get a number that ends in 8, and that ends up being the answer. Now, as I said, I was going to show you two different ways, and when I was doing this way and I got to this point, it was like, how do I know if x is the largest? So I said, and I wasn't thinking at the moment, and you're trying to go as quick as you can to get to later problems, the clock's starting to tick down, and I said, well, something else I happen to know about squares is that the difference in consecutive squares is the sum of their bases. So I said, well, if these were consecutive, and are they? I don't know. We don't know that, right? If they were consecutive, this would need to be, because that's the difference. If they were consecutive, that's the difference is the sum of their bases. However, if you don't know what I'm talking about, here's an example. 3 squared to 4 squared, the gap between 9 and 16 is 7. But that gap is equivalent to 3 plus 4, the sum of the bases of the perfect squares, okay? Or their square roots, if you will, but bases is easier to say. Okay, so then because of that, I said, well, then this sum is always odd and that sum is even, so if these are squares, they can't be consecutive squares because they would have to have an odd sum, so they must be separated by at least 2. This is another thing that I've taught myself over time. When you have a difference in squares that is exactly 2 rather, let's say I've got x plus 2 squared and I subtract x squared, you can prove that this is 4x plus 4, which is 4 times the number in the middle. To see what that looks like with numbers, I'll give you an example. From 10 squared to 12 squared, the gap is 44. And 44 is equal to 4 times 11, the number right in the middle of 10 and 12. And that, of course, will always, you have an even number because you're multiplying by 4. So I said, well, if this was that situation, then what would I use? 4 times what is 2560? It's clearly divisible by 4. And you say 4 times, and it would be 640. 4 times 64 being 256. If you don't know why, 2 to the 6 times 2 squared is 2 to the 8th, and 2 to the 8th is 256. And then you just put the 0 on the end. Okay, so then that would mean 640 would have to be the middle number of my 2 perfect squares, so they would need to be 639 and 641, and that is, of course, the same number that we found over here. If you go any larger, like you tried to achieve something larger than using these two, the next thing up, if I did between 640 and 642, let's say, then the product of 4 times these two squares, if you don't understand, 640 squared, 642 squared, their difference now would be 4 times 641, which is more than this number. So there's no way that you could get any larger with your perfect squares. If you dropped lower, like let's say I wanted to make it 642 squared, but I was just going to lower the other square to something farther down, like 639 squared. The problem is the gap is just bigger now. It's even bigger than it was before, so there's no way you're going to have a gap that you need of 2560 between your squares. So if you've worked with that concept a lot, this wasn't hard to conclude that 641 was the larger of the two squares, and you reason very much the same at the end with the 1 minus the 3. So that's two different ways. Hope you enjoyed it. Let's get to the next one. All right, and the last one of the set of rapid fire for AMC 12A, problem 6 through 10. Let alpha, this is problem 10, let alpha be the radian measure of the smallest angle in a 3, 4, 5 right triangle. Let's go ahead and draw that. I'll put the smallest side here like this, and 3, 4, 5, alpha there. Okay. Let beta be the radian measure of the smallest angle in a 7, 24, 25. So same thing, we'll make the small side over here, and I have beta and 7, 24, 25. In terms of alpha, what is beta? Now I thought about this for a bit and was just like, what? I can't think of how to start. Like, how do you get them to interact? They need to interact some way in some kind of equation. But I've tutored a few students in pre-cal, and I thought I remembered there being some relationship between the 724.25 and the 345. Was it double angle? Was it angle addition? Was it half angle? Couldn't remember. So I just guessed, like, let's see what happens. This is probably not the best way to solve it, but sometimes that's what you do. You just try things out, see what works, see what doesn't. Maybe you'll generate, I really thought I would just generate some new piece of information and kind of see what it looks like. So I just said, well, just out of curiosity, what's sine of alpha plus beta? Let's look. So I said, and I'm just going to call it A plus B now because they're easier to write, and I'm sure you probably did the same thing. So A plus B would be what? It's SCCS, which is sine A cosine B plus cosine A sine B. Okay, you need to memorize your identities. You have to know your trig identities. They should be in your small notebook. I did not cover these in all of my small notebook classes this year because they're considered kind of standard. It's like, do I know 3 times 4 is 12? You know, do I know a 30, 60, 90 triangle? For AMC 12 students, your trig identities are just about mandatory, so you should have them in yours. And then I see what happens. What would this be? Sine of A is 3/5. So we get 3/5, okay? I have no idea what we're doing or how it's going to work out. Like, I don't know what we're trying to achieve here. I'm just seeing what happens. So 3/5 times cosine of B, which would be 24 over 25, plus cos of A, which is 4 over 5, times the sine of B, that's opposite over hypotenuse, 7 over 25. So I can see we're going to get fractions that work well. We get 125 as our denominator. And up here we get 72 plus 28. Those are like algebraic complements. They add to 100, not complements like 90-degree complements. Call it algebraic complements when it adds to a multiple of 10 or a power of 10. So 72 and 28 add to 100. That's 4/5. So wait a minute, the sine of alpha plus beta is 4/5, but we have a 4/5 here. The angle what's this angle have to be then? This angle has to be alpha plus beta, because when we added them and took the sine, it came out to be opposite of that. Oh, that's what it is. And since this is 90, you now knew that 2 alphas plus beta, or as I'm going to say, 2a plus b is equal to 90. You're like, why are you using 90? They said radians. I say that my first language was degrees, and I had to learn radians as a second language, and so my native tongue is degrees, and I don't care if you like radians more. I think I will stick with my degrees, and yeah, we can always write it how they want to see it at the end. So I just go back to degrees as a default. It's easier to think about, really. So now what? 90, I want what? Beta? What is, in terms of alpha, what is beta? In other words, solve for b. So it's 90 minus 2 alpha, which in our case is going to be pi over 2 minus 2 alpha. Sometimes, like, you don't know what you're doing, just try something. I got really lucky. Here's my paper. You can see it when I solved it right there. Yeah. So I just tested it out, and it worked. Yeah. So, sometimes you get lucky on the test, intuition, all that kind of thing. But I mean, what else are you going to do? You could try double angle. You could try, but you needed something where A and B were together. So the natural thing would be, what if I added them? And since we're talking about we weren't talking about it yet, but we said that the smallest side, the angle opposite the smallest side, right? What does it say? The radian measure of the smallest angle, which is opposite the smallest. So you're talking about sine and cosine. It just seems natural to get them together and see what happens. It might have also worked if you did cosine of A plus B. I have no idea. That would be CCSS and the opposite sign, and we could try it right now, but we're not going to because it's late. Going to get to problem 11.